This is lesson 5, which we did not get to in class, and it starts out with the meaning of nth root. When we talk about the nth root of a number, what do we mean? Well, if we talk about the square root of a, what we mean by that is the number that you multiply by itself to get a. So the square root of a times the square root of a is a. That's the definition of square root. Cube root is the cube root of a would be the number you multiply by itself 3 times to get a. So cube root of a times cube root of a times cube root of a is a. The fourth root of a would be the number you multiply by itself 4 times to get a. Fourth root of a times the fourth root of a times the fourth root of a times the fourth root of a is a. The fifth root of a, as you would expect, is the number you multiply by itself 5 times to get a. So fifth root of a, fifth root of a, fifth root of a, fifth root of a, however many times, 5 times, will give you a. So the nth root of a is just the number you multiply by itself n times to get a. Sometimes when we're doing algebraic manipulation, we like to express roots as fractional exponents or rational exponents. So the square root of x is also written x to the 1/2. The cube root of x can be written x to the 1/3. The fourth root of x can be written x to the 1/4, and so on. So here's a problem. Square root of x cubed y times the fourth root of xy cubed. We could change these root signs into fractional exponents, and we'd have x cubed y raised to the 1/2 times xy cubed raised to the 1/4. We could then use the rules for exponents that tell us a power raised to another power. You multiply the exponents. So here, if we multiply the exponents in the first parentheses by 1/2, we're going to have x to the 3/2, y to the 1/2. And then in the second set of parentheses, we can multiply the exponents there by 1/4, and we will have x to the 1/4, y to the 3/4. Then we can add the exponents on the like bases. So on the x, we have 3/2 plus 1/4, which is going to be 6/4 plus 1/4 is 7/4. And then for the y's, we have y to the 1/2 times y to the 3/4. So if we add 1/2 plus 3/4, that's 2/4 plus 3/4, which is 5/4. Here we have a to the x over 2 times y to the 2 minus x, all raised to the 1/2, over a to the 3x, y to the negative 2x. So we can do this many different ways to get it simplified. It just kind of depends on what comes to your mind first. You might want to distribute that 1/2 to this exponent on the y. And then you could also bring up from the denominator up into the numerator. You could bring the a to the 3x and the y to the negative 2x. When you bring them up to the numerator, you change the sign on the exponents. And you can do that with any factor in a fraction. If it's a factor of the whole numerator or the whole denominator, you can move it up or down and change the sign on the exponent. So now I add the exponents on the like bases. So a to the x over 2 minus 3x, you're adding the exponents on the a's. And then for y, you've got y to the 1 minus 1/2 x plus the other exponent 2x. And then if you get common denominators and add those up, you're going to have a to the negative 5x over 2 and y to the 1 plus 3x over 2. On this problem, it's x to the negative 2 plus y to the negative 2 all over xy, all of it raised to the negative 1. You have to be careful here because you can't move x to the negative 2 down to the denominator and change the sign on the exponent. And you can't do that with y to the negative 2 either. You can only do that when you're dealing with a factor. Factor means multiply. Multiplication is the inverse operation of division. The fraction line means division. So you're allowed to move factors from the top to the bottom and bottom to the top, changing the sign on the exponent, but you can't move addends. These are addends. So you can't start moving them around the fraction. Only factors can be manipulated that way. So you could move xy to the negative 1, that whole thing up to the numerator, and change the sign on that exponent and make it positive 1. But you definitely cannot move the x to the negative 2 down and call it x squared in the denominator. And same thing with the y to the negative 2. You cannot move them that way. Well, I'm telling you, you can't do that. I put that there just so you know. You're not allowed to do that. You can't. All right, so what you have to do is you're going to have to You can bring the xy up into the numerator and call it xy to the positive 1, and then you have to write x to the negative 2 as 1 over x squared, and y to the negative 2, you have to write it as 1 over y squared. And you're adding those two fractions together. Now you can distribute the xy, and you'll have xy over x squared plus xy over y squared, and then you can cancel the x in the first one, and you'll have y over x plus x over y, and then you can get a common denominator xy, and you will have y squared over xy plus x squared over xy, and then you can write this as x squared plus y squared over xy, which looks very familiar. It looks a lot like the original problem, but it is very different. All right, now you have 3 times the square root of 3 halves minus 4 times the square root of 2 thirds plus 2 square root of 24. First of all, I need to rationalize the denominators in the first two terms. You cannot have a radical in the denominator of a fraction. And you can't have a fraction inside a radical. So you would break these up. You'd have 3 square root of 3 over square root of 2 minus 4 square root of 2 over square root of 3 plus, and then just to get rid of that perfect square that's in the square root on square root of 24, you can change that to 2 square root of 4 times the square root of 6. And so here you'll rationalize that denominator by multiplying the top and the bottom by the square root of 2. And this is not optional. You have to do this. Cannot leave a radical in the denominator. Well, you're going to have to do it to the other fraction also. So you're going to have to multiply the top and the bottom by the square root of 3. And then when you rewrite this out, you'll have 3 square root of 6 over 2 minus 4 square root of 6 over 3 plus 2 times square root of 4, which is 2, times square root of 6. And then you will have 3 square root of 6 over 2 minus 4 square root of 6 over 3 plus 4 square root of 6. Then you're going to want, since you have all these square root of 6's here, you're going to want to go ahead and get a common denominator so that you can add all those like terms together. They're kind of like terms. They all have a square root of 6. So you're going to want to get your common denominator, and then you will have 9 square root of 6 minus 8 square root of 6 plus 24 square root of 6 over 6. And then when you add that all up, you're going to get 25 square root of 6 over 6, and that is the simplest way to write this. So here you have the quantity square root of 2 plus square root of x times the quantity 1 minus square root of x, and you're just going to use the distributive property here. Square root of 2 times 1 is square root of 2. Square root of 2 times square root of x is the square root of 2x. You're subtracting that. And then square root of x times 1 is square root of x, and then minus square root of x times square root of x, which is just x. And now you want to rearrange it so that you're going by powers of x. Negative x plus, and then you have two terms here, the second term and the third term, both have a square root of x in them. So you could factor out that square root of x and write it as 1 minus the square root of 2, that quantity times the square root of x, and then your final number is the square root of 2. The reason I'm writing it this way is because usually whenever you write an expression like this that has powers of x in it, you want to start at the highest power of x and move your way down to the lowest power of x. So this is x to the first power, this is x to the 1/2 power, it's all the terms involving x to the 1/2 power, and then square root of 2 has x to the 0 power, which is just 1. So it's just a notation kind of thing. It's no more correct as far as the value of this thing than the second line is, but it's just the way you would normally write this in order of powers of x. All right, remember imaginary and complex numbers. Remember that I is the square root of -1. It's an imaginary number. It's not a real number. It's not on the real number line. But whenever you have a square root of a negative number, you need to use this notation to work with it algebraically. So because I is the square root of -1, that means that I squared is -1, because the square root of a number is the number that you multiply by itself to get that number. So square root of -1 times square root of -1 is -1. That's the whole definition of square root. So you always have to convert any negative square root to a multiple of I. So if you have the square root of -5, you can't write it square root of -5. You can't leave it like that. You have to write it as the square root of 5 times the square root of -1, or the square root of 5i. Know the powers of I. So remember, if I is the square root of -1, then I squared is -1. That's the whole definition of square root. I cubed is -1 times I, so negative I. And then I to the fourth is -1 times -1, because it's I squared times I squared, so it's just 1. And then the cycle starts all over, and it just keeps going. I, -1, I, 1. I, -1, I, 1. As you go up in your powers, sorry about that, it just keeps going around. So I to the 5th is going to be I again. I to the 6th is -1. I to the 7th is -I. I to the 8th is 1 again. I to the 9th is I to the 10th is -1, and so on. An imaginary number is a multiple of I, such as 5I. Okay, so that's an imaginary number. A complex number, it has a real part and an imaginary part. So a number like 5 plus 5I is called a complex number. It's not called an imaginary number. An imaginary number just has an imaginary part, so 5I. But a complex number has a real part, 5, and an imaginary part, 5I in this case. Note, if the real part is 0, we can still say the number's complex. So you can call 5I a complex number, but you can't call 5 plus 5I an imaginary number. You have to call it a complex number. 5I, you might say, is purely imaginary, but you could still call it a complex number. Just say the real part is 0. It's just a vocabulary thing. 3I cubed plus 2I to the 5th minus 3I plus 2I squared. If you wanted to add this up, you would use your powers of I to simplify it. So you're going to have 3 times -I, because I cubed is -I, 2 times I to the 5th is I, minus 3I plus 2 times I squared is -1, so that's 2 times -1. So when you simplify all this out, you're going to have -3I plus 2I minus 3I, which is going to be -4I, and you're going to have -2 for your real part. So you've got -2 minus 4I. You've got your real part first. You got your imaginary part second. That is how you're supposed to write a complex number all the time, every time. Do not write it in any other way. Write the real part first, imaginary part second. You have the square root of -3 times square root of 4 plus 3 times the square root of -2, square root of -9 plus square root of -16 plus the square root of 16. I think that might be wrong in your notes. There's supposed to be a plus sign right here. One thing you cannot do is this. You cannot just treat this like any old real numbers. You can't treat this like these are all real numbers and just multiply the radicands. And, like especially in the second term here, you can't multiply into the square root of -2 times the square root of -9 and get the square root of 18. That is not a true statement. So these are not real numbers. You can't treat them like real numbers. You have to change it to I notation, and then you can start doing your algebraic manipulation. So this is a definite no-no. Do not do that. All right, so whenever you see a negative number in the square root sign, you need to change it to I notation. So you're going to, for the first term, you're going to have the square root of 3I times the square root of 4. Plus the second term is going to be 3 square root of 2I times the square root of 9I plus square root of 16I plus square root of 16. Okay, now you can start doing the multiplication. So for the first term, you're going to have 2 square root of 3I. And for the second term, that square root of 9 can now become 3. So 3 times 3 is 9. And then you're going to have the square root of 2, and you're going to have I squared, which is -1. So that's going to show up as a minus sign in front of the 9, which you wouldn't have if you had done it the other incorrect way. All right, square root of -16 is just 4I, and then the square root of 16 is 4. And remember, so there, that is with that I squared changed to -1. And then remember, for your final answer, you need to write the real part first. So that's 4 minus 9 square root of 2. Those are the real numbers in this expression. And then the imaginary part second with the I factored out. So 2 square root of 3 plus 4, and then the whole thing multiplied by I. So real part first, imaginary part second. So it's something, some real number, plus something I. That's how a complex number has to be written. Similar figures have congruent angles and proportional sides. You know that from similar triangles, but you can talk about that idea with any other shape too. So in this situation, you have two rectangles where the scale factor between the two rectangles is 4. What that means is that the ratio of the side lengths from the smaller rectangle to the bigger rectangle, that ratio is 1:4, or that's a one-dimensional measurement. If you want to talk about the ratio between the areas of the two figures, you square that ratio. So the ratio of the area of the smaller one to the area of the bigger one is the ratio 1:16. Okay, this problem says, example 5.9, one circle has radius r and the other circle has radius 3r/5, or 3/5 r. What is the ratio of the area of the first circle to the area of the second circle? So the first circle has radius r and the second circle has radius 3/5 r. So the scale factor between those two radii lengths between these two circles is 3/5. You would multiply the radius of the first circle by 3/5 to get the radius of the second circle. So the question is, what's the ratio of the area of the first circle to the area of the second circle? All right, so that scale factor, we need to make sure when it says the area of the first circle to the area of the second circle, that we're doing that ratio in the right order and that we don't do it upside down. So just to make sure we've got it clear, I'm just going to put up this little table where we have the ratios of the length of the radii, the ratios of the area of the circles, and then the ratio of the volume of the spheres. So the ratio between the radii length is 1:3/5 if you're talking about going from the first circle to the second circle. That means the areas, the ratio of their areas from first circle to second circle is 1 squared to 3/5 squared, because area is two-dimensional. So that ratio from area of the first circle to area of the second circle is 1 to 9/25. If we were talking about volume, the ratio would be 1 cubed, or 1 to 3/5 cubed, or 27/125. So that ratio would be 1 to 27/125. So the question is asking for the area, the ratio of the area of the first circle to the area of the second circle. And so we said that's 1 to 9/25, which is 1/9/25, which is 25/9. Okay, this says find the length of the diagonal that connects corners B and H in the rectangular solid shown. So you have this rectangular solid and you're looking for the length of its diagonal, which goes from the front lower vertex up to the top back vertex. So it's going through the space inside that box. So we're going to do that by using the Pythagorean theorem, but we have to deal with a couple of different triangles. So first of all, we're going to deal with the triangle that we can make on the base of this rectangular solid, BGC or BCG. So that's the triangle that's flat on the table, and it has legs X and Y and hypotenuse BG. So we can find the length of that hypotenuse of this triangle. We'll just pick the triangle up and put it up here, and we'll use the Pythagorean theorem. So BG squared equals X squared plus Y squared. That's the Pythagorean theorem. So that means that BG, the length of that hypotenuse, is the square root of X squared plus Y squared. So we can put that over there on that flat triangle so we can see it. And now we can look at triangle BGH to find that hypotenuse. And GH is just the same as Z, which was on the other side of the box. So now we know the two legs of that triangle, and we can find the length of BH. So using the Pythagorean theorem on that triangle, we're going to have BH squared equals the long leg squared, square root of X squared plus Y squared, squared, plus the short leg squared, Z squared, And if you square that square root, just to simplify it, that equals x squared plus y squared plus z squared. So if bh squared equals x squared plus y squared plus z squared, then bh is just the square root of x squared plus y squared plus z squared. So that's the length of bh, and that's going to be the length of the diagonal for any rectangular solid like this. If you draw the diagonal from a front vertex to a back vertex through the space inside the box, that length is going to be the square root of length squared plus width squared plus height squared.